try to address the concepts of groups, rings, fields, and actually put together a small video diagram to explain those concepts. I mean, just one cheat sheet. So virtually the same concepts that we discussed in the first 4 slides of lecture 1 are portrayed here. So just a quick way for you to see what is considered a field, what is considered a ring, what is considered a commutative ring. And I gave some examples using the set of integers, the set of real numbers, and also classification of some types of sets that you're well familiar with, such as with the set of integers Z. So virtually consolidated all that information in one slide that you can always use for reference to understand what is a group, what is a commutative ring. So this is just, it's the same material, but in a more visual form. So I mean, it's in a visual form. Okay. So we almost got done with the first presentation last time, and there were 2 aspects that we did not cover. Those 2 subtopics are distinctive features of lattice-based cryptography. How is it different from conventional types of public key cryptography that are based on discrete logarithm problem, or that are based on trapdoor functions such as RSA. So I'll quickly explain what are the conceptual differences between the 2 from the crypto perspective. And so briefly discuss the fact that lattices use slightly different probability distributions as compared to many other crypto schemes, such as the ones I mentioned. So let's quickly go to the closer end of that presentation, so we can quickly those topics. One of the, I would say, reasons why lattice-based cryptography has not been widely used, I mean, of course, one side is the math behind it, and it's being developed. The other side is the complexity that's involved in lattice-based cryptography as compared to conventional gut fields, in other words, regular discrete logarithm problem or trapdoor functions. And there are certain things that are very similar in the formulation of the problems. For example, if one looks at the problem of finding the secret polynomial or secret lattice in the LWE problem that we discussed in the previous lecture, we'll see a lot of similarities with the discrete logarithm problems. So conceptually, there's the problems we're going to discuss within the concept of within lattice-based cryptography is certain hard mathematical problem, which is somewhat similar to RSA and discrete logarithm problem. But the 4 major differences between that distinguish based cryptography from those, I'll call them conventional approaches to public key cryptography. So one distinctive feature is here we deal with finitely generated groups, and simply speaking, lattices are groups, and lattices are formulated using the basis vectors. And you remember that the representation of the lattice uses the set of integers and a set of basis vectors that are used, and you can represent any lattice using linear combination, linear superposition of the basis vectors with some integer coefficients. And this type of mathematical structure is highly different from the conventional modular arithmetic which we use in the case of discrete logarithm problem. It's also different from elliptic curve cryptography. So in other words, we're dealing with certain special groups that are generated using, in this case, certain basis vectors. Another concept that's very important, noise, and we'll discuss this concept in more detail in further lectures, play a very important role in the security of lattice-based crypto schemes. Actually, when you introduce the noise, and you remember we discussed the learning with errors problem in the previous lecture, introduction of noise that makes the problem hard, and there is a positive side that introducing the noise makes the security harder, but also there is a I would say there is a drawback of this approach in the sense that we need to make sure that the noise never causes our for example, polynomial to go over a certain modulus that we deal with. In other words, we need to make sure that the decryption is always correct, and this plays an important role there.
So if I word it edgewise, at least from experience building these things, I'm sure some of the guys out in Spaywar will, or SSC pack will agree with this, or at least validate what I'm saying, is that this whole issue of noise management is in some sense the central issue associated with building, designing, and a lot of these protocols built on Lattice crypto, whether it's for homomorphic encryption, proxy re-encryption, it's anything and everything you want to do with this that's more than just a basic public key crypto system. So one thing, this is going to be an ongoing theme, of course, you know, a lot of these discussions, a lot of these things we're going to be having, building over the next couple of years, is understanding how the noise, estimating noise, how to generate noise. And the noise generation, of course, is a major engineering challenge in and of itself. And I know the NSA probably has teams and people, well-funded people, actually focusing on these issues of noise generation also. And so, like the Remainder transform, the discrete Fourier transform, and these other kinds of things that we discussed, this noise issue is going to be a major ongoing theme in a lot of our conversations, a lot of our research going forward. So that.
No problem. And actually, part of the analysis of crypto schemes, and which we'll discuss in future lectures, will be derive the noise constraint, noise inequality, which guarantees that our scheme is actually is correct. In other words, that the decryption is done properly. So, so any design of a crypto scheme in noise-based cryptography deals with formulating noise constraint, I would say correctness constraint that is based on noise, and also the security is based on noise as well. So that's and that definitely distinguishes lattice-based cryptography from other approaches that you're well familiar with. Probability distributions play a very important role, and we'll talk about it a little in more detail at the end of this lecture. But generally speaking, in addition to uniform distribution, random distribution that everyone is familiar with, in this case, we also deal with discrete Gaussian distribution, and actually plays a very critical role in defining so-called small polynomials. So discrete Gaussian distribution plays a very important role. Again, this is a feature of this particular approach of lattice-based cryptography. And the hardest part that when I build a crypto scheme that runs based on lattice-based cryptography, have to deal with multiple parameters, generally speaking, 6 or 7 parameters. And the selection process for those parameters is not sometimes intuitive. We have to formulate certain inequalities. We need to make sure that the security is achieved. We need to make sure that correctness is achieved. And we also have to keep in mind the hardware optimization aspect. So the parameter selection is an important part in designing and implementing any crypto scheme based on lattices.
So I want to get a couple words in edgewise associated with this. This is, in some sense, the other major theme we're going to be wrestling with. And, you know, some of you are going to be looking at some of the more theoretical papers and maybe taking some of the high-level views of cryptography based on Yuri's class or some of the other, or other guy's class that I think is offered by Professor Kortmola. It's cryptographers talk about parameter selection. Cryptographers, theoretical cryptographers love to talk about parameter selection. Well, that's all well and good, which is generally the equations that go into what they call cryptanalysis. So what the traditional academic cryptographers call concrete parameter selection, which is choosing the numbers themselves. And so sometimes, you know, you see these kind of, 1984 type doublespeak sometimes from the academic community, parameter selection versus concrete parameter selection. And really the things that we're going to worry about in this group as we're building things is the concrete side of the stuff. This analysis is important where they care more about order of computation and sizing. This is an anecdote that one of my colleagues, I was a system for DARPA with Chris Piker from Georgia Tech. This when I was in industry, and we had to get this DFT working in hardware, and they're having trouble with security issues, and he basically says, well, double the dimension. And it's like that's basically pushing a 16,000 point DFT to a 32,000 point DFT, when there's probably even less circuits than we actually needed for the number of dimensions on the actual hardware we were doing themselves. And so this is, like I said, some of the mindset that we're going to be dealing with as we talk about some of our academic colleagues and transitioning the academic results into more implementation-oriented results, is just what we'll be focusing on here. And it said that a lot of the traditional concrete parameter selection, for example, the RSA or ES, is just like a bit width, mentioned doing things, and we'll get into this more deeply later today or next session. Things like the computation, bit, talking about things like ring dimension and stuff like this. And so there's a whole host of things that we're going to be wrestling with, and a lot of them we're balancing, and we're like squeezing a balloon. That if you want to get one thing down, something else might pop up someplace else. But this is, like I said, ongoing issues that we actually get creative about building these things.
Yes, and I would like to add something to this. The conventional security analysis for RSA is based on so-called practical security attacks. Generally speaking, you try certain attacks and you analyze how secure the system is, and secure more from the performance perspective, how much time it would actually take to break a certain crypto scheme. So the traditional approach is based on so-called practical security attacks. The lattice-based crypto is based on concrete security, which is a theoretical analysis that goes back to those NP hard problems that we discussed. So its analysis is actually based on theoretical studies and mathematical studies and selection of special parameters such as Hermit factor. So for lattice crypto, we can use both theoretical methods and practical methods. That's right. Just simply speaking. And just a quick comment on probabilities. I want to make a very important note that in the case of lattices, we will deal with distributions on certain lattice points. Sometimes we may deal with distributions on overall lattices. And from a practical perspective, distributions on lattice points is what we're going to focus on, so more localized regions. And just a second, I think we went. Most important distribution in formulating the actual crypto schemes in the case of lattice-based cryptography is the discrete Gaussian distribution. And this distribution is illustrated here. I'm sure some of you are familiar with the regular continuous Gaussian distribution. So this is it's a discrete equivalent, and many themes that we will discuss will be based on lattices chosen, so-called full lattices chosen based on this type of distribution, which is unique to this type of field, the field of lattice-based crypto. Everything we have for lecture 1, so the reference material where you can find additional information is listed here, and I believe Kurt also sent one of the conceptual papers on learning with errors problem. We're going to move to lecture 2, focus on ideal lattices. So this lecture will be more practical compared to the first one, and we're going to introduce the concept of cyclic lattices, ideal lattices, and then we'll discuss the mathematical problem that will be cornerstone of the crypto schemes we'll be developing, and that problem is Ring-LWE. And of course, then we'll discuss certain concepts related to polynomials, which are equivalent to ideal lattices.
Okay. You said in previous slide that Gaussian distribution. Does that mean all the points that are related vector that have defined Gaussian distribution?
Polynomials, when you perform, and it will be much easier to see when we discuss certain crypto schemes and the Ring-LWE problems. Certain polynomials involved in computing the private key or public key are actually generated based on discrete Gaussian distribution. So, and the noise, for example, that will play a very important role is will be generated using discrete Gaussian distribution. So a lot of polynomials or equivalently ideal lattices will be generated based on this type of distribution. But when we look at examples, it will be easier to see. We asked in the first lecture lattices, and everyone probably has some kind of visualization in their head right now that the lattices are represented as matrices. So there is a matrix to represent all the vectors in the basis, and operations are generally performed using that matrix. This is a practical way to reduce that matrix to of the same dimension. And ideal lattices is a mechanism that allows us, and cyclic lattices as well, to reduce the complexity of dealing with a matrix to a much more efficient problem of dealing with a vector. So that's why ideal lattices were introduced. And a couple of comments. So lattices are groups in terms that we discussed in the previous lecture, and ideal lattices are ideals defined for those groups. So simply, those are subgroups that have certain important properties. We can call it a cyclic property. It's a subgroup that can be used to efficiently perform operations dealing with lattices. General motivation of going from lattices to ideal lattices is to develop efficient cryptographic primitives. So that's the only motivation there. In original research, the initial research in this base crypto was very interesting from the theoretical perspective, as you have NP-hard problems, but was highly inefficient. And it's only after introducing ideal lattices, also cyclic lattices, this type of cryptography became actually practical. Start with first the definition and actually an example of cyclic lattices. Cyclic lattices and ideal lattices are very similar to each other, as we'll see later. And cyclic lattices were used for early crypto schemes such as the conventional NTRU scheme. A general idea is that, again, dealing with a matrix, we can perform all operations a certain cyclic lattice, a vector, not a matrix anymore. And what are the operations that are defined on cyclic lattices, and how do they look? So, we have two. So we have two vectors defined on cyclic lattices, and when we look at the operation of adding one vector to another vector, all we're doing is we're simply performing component-wise addition. We're adding each component to its corresponding component to yield the result. For example, -1 plus -7 is equal to -8. So component-wise addition. For in that cyclic lattice, we have operation of negation defined, which simply means replacing the signs of the integers in the vector. Why they're called cyclic, and the very convenient property that they have is you can perform a cyclic shift of vector v, I mean of a certain vector, by simply moving the layer of the components around, like wrapping them around. As you can see, we move -4 here, and then everything pushes either -1, -2, and 3. So here you operate in a cycle. And interesting enough, this type of definition of cyclic lattices is equivalent to ideals in polynomial rings of certain type. So in other words, these cyclic lattices can be represented as polynomials. But the polynomials where the coefficients are taken from the set of integers, and the polynomials where we perform the division by x taken to the power of n minus 1. In other words, we have this case, so we divide any polynomial operations that we perform, we divide them by that base polynomial. So the important property is that cyclic lattices are equivalent to ideals in polynomial rings. And what it also means that we can perform any operations with the same operations with ideals that we can do for polynomials. And polynomials are, I mean, is a very efficient mechanism for performing computations, and we'll discuss why. We'll discuss some examples. So the same vectors that we looked at in the past can be represented as polynomials. Coefficients are the actual values of the vectors. So all this is we're simply representing polynomials as vectors of integers. That's both of them are equivalent to each other. Within the operation of negation, again, means simply multiplying the polynomial that we have by -1, and it will immediately give us the result. And the same way, we can define the operation of a cyclic shift, which in case would mean multiplying the polynomial v by just a linear, simplified polynomial, just a linear term. And if you perform this operation and followed by division by xn minus 1, will have the same type of vectors that were produced by cyclic shifts. So generally speaking, if we in terms, so let's say -4 multiply x taken to the power of 3, when multiplied by x, so the power of x becomes 4, and in this case we're dealing with the case of n equal to 4, divide this term, the polynomial, and I'm sure you remember from high school algebra, to perform polynomial division, you simply add the coefficient to make sure that at the top you have x to the power of 4 minus 1 multiplied by some factor, and then so you add a certain term and then you subtract certain term. After that operation, what you will get is you will get the coefficient corresponding the value, I mean, to the cyclic shift of within that vector.
So it's actually quite strange when you bump into it the first time. So I didn't really have, when I first started doing homework encryption about 4 years ago, I really didn't have the necessary mathematical background. This was always kind of a story, actually, how it worked. And so as we started to conceptualize about it was that there's, almost in some sense, two moduli when you're doing these manipulations. There's moduli associated with just the most of the ciphertext, and moduli associated with this dimensionality that's going there also when we're doing things like multiplying ciphertext, doing the equivalent like taking these, basically multiplying these ciphertexts. Which, anyway, sorry to interject.
Yeah, so intuitively it may look a little bit strange because I'm sure everyone understands how to apply the mod operation to the ciphertext. So in other words, when instead of z, we have z with a certain subscript of, let's say, 13, just as an example that we considered. In other words, everything's limited values are limited to 0 to 12, from 0 to 12. In this case, we also have the polynomial division, but the polynomial division for types of polynomials such as x to the n of minus 1 is very easy, and again, you can just go exercise. It's actually very easy to you simply add a term, and then you subtract a term, and then you have something that divides by x taken to the power of 4 minus 1. So in other words, it's the integer part, so it can be removed from our consideration, and whatever is left as the remainder is used. In other words, it's term by term. So we perform the division, polynomial division, for each term independently, just to make it simple. That's what produces the result. So this type of cyclic lattices that we considered here were actually developed in, I think, in late 90s, started 98. The NTRU scheme that some of you may have already heard was actually developed based on this type of cyclic lattices. So in other words, the polynomial basis there was x taken to the power of n minus 1. And what's very important about those initial schemes is that, first of all, operands on polynomial are highly efficient. And second, that in some indirect way, the NTRU scheme was linked to some of the lattice problems, but not as, but not in a such convincing manner as it's done for the case of ideal discussed next. So we're getting to the concept of ideal lattices. It's very conceptually speaking, the goals are the same. We want to reduce matrix to a vector, but we use a different polynomial. We divide by a different polynomial, and there are three important properties that our case of polynomials have to satisfy, and those properties enable us to directly use the lattice the lattice problems that we discussed in the first lecture. So in other words, the use of those three properties allows us to fully take advantage of mathematical hardness of shortest vector problem, closest vector problem, and in this case, it's generally the shortest vector problem, but it's polynomial approximation that's considered. So this is driven by security, but at the same time, efficiency, because we will still be dealing with vectors instead of matrices. And types of polynomial, I'll probably, the polynomial we divide by, there are two very important types, and one of them is represented using a power of 2, so it's xn plus 1 when it's power of 2. Another case corresponds to the polynomials there is a subscript n is prime. So the case of prime and the case of 2 to the power of n, very similar to what we've seen in the cases of regular number theory, of elliptic curve cryptography. Those are the two types of polynomials. And we'll explain later in further lectures which ones are most appealing, which ones, why we use them. So the choice of polynomials is extremely important. Now let's look at the definition of ideal lattices. Those x, in this case, we're looking at the case of power of 2, when n is a power of 2. So it's a specific case when we're dealing only with powers of 2. And xn plus 1 ideal lattices are equivalent to ideals in polynomial rings. In this case, we divide by the polynomial xn plus 1. So that's in contrast to xn minus 1. And simply speaking, it gives us better security. So that because it allows us to directly relate to to directly trace back to the lattice problems that are NP hard. Look at the operation of addition of using these ideal lattices the difference is very to what we discussed. It's actually it doesn't change, and you can easily verify this. The operation of negation is the same as in the case of cyclic lattices. The operation of cyclic shift or multiplying by x in this is different. Simply speaking, we perform the cyclic shift. In other words, let's say we have minus x to the power of 3. When we perform the cyclic shift, in other words, multiplication by x and division by x taken to the power of 4 plus 1, the sign of the coefficient changes. It becomes the opposite, and again, it's very easy to show it by performing term y. So by taking the term and dividing by x taken to the power of 4 plus 1. So all that can be performed, but the advantage of dealing with ideal lattices is that you don't have to perform polynomial operations. You simply deal with vectors, and you simply manipulate either coefficients or the values of polynomials, which we'll discuss for evaluation and presentation. So ideal lattices are very similar to cyclic lattices that have been used, for many years, but they trace back to the security of less problems. And ideal lattices is what we're going to focus on probably in the next several seminars. And Ring-LWE is actually based on ideal lattices. Now that we find ideal lattices, revisit the main inefficiency that we observed in the case of LWE, learning with errors problem. And the main inefficiency was that to generate every certain vector at the end, we needed to use n-dimensional, in this case, 4-dimensional vector to generate each component of the vector. And this means that we had to work with the matrix to get the full vector for a certain lattice we're dealing with. And general reasoning behind choosing ideal lattices is the way to choose something more efficient where you can generate one vector and use that vector to get the complete resultant vector.
So it's a term of ciphertext expansion type issue, more compact representations of data, or is it something where it's a more efficient computation?
It's more efficient computation, to put it simply, and we only need to generate one vector to perform all operations on this slide. And I'll show you in a minute.
Just
yes,
questions, right?
Yes. Actually, and I included
a wonderful slide.
Yeah, it's a wonderful slide. The reason why I included it and is because it contains certain.
Right.
Yeah, this is again. My goal here was also to basically to note that LWE survey paper that was included, and this is so the general idea is when you deal with to generate a vector, you to generate n vectors in that space. In other words, the complexity of that operation is going to be n squared. And reasoning behind ideal lattices is, what if we get a certain vector initially? So in this vector A1, go A1 to AN, and we generate all other vectors using the same components with virtually just a cyclic shift of components. And this is to reuse the components of the vector to formulate all other vectors. And this reduces the dimension of the problem we're dealing with. So in other words, dealing not with n squared elements in this case, but we're dealing with simply n elements. And then I included it actually from this paper because it's that idea very well. So we generate all the components for the n-dimensional vector once, and then we use those components by performing certain cyclic shift operations, and we can still achieve almost the same level of security, which is obviously topic of mathematical proofs. For those of you who are interested, there is a Ring that L.WE survey paper discusses this type of information in more detail.
So that's a survey paper that it basically was co-written by one of my long-term collaborators, Chris Piker from Georgia Tech. And I vouch for it's, I'm a big fan of that paper myself, but we'll be going over that sometime eventually.
Yes, and this is the reason why I included the action. Right? Simply speaking, if we go back to our problem, instead of generating a new vector, so for each row in this matrix, we can reuse the coefficients, and I'm referring right now to row 2, of that initial vector by simply forming cyclic shift of components. And see all the first 4 vectors, same coefficients, they can be used to generate the complete vector on, the resulting vector, which is used for the learning with errors problem. So that's general logic. Rather than generating a new vector, a new coefficient every time, we actually generate it once, and then we reuse the coefficients in a cyclical manner. That's the general idea. And a lot of papers show that from the security perspective, we are still able to rely on proofs that are related to lattice problems that are NP-hard. So lattices to ideal lattices is the defined step. So we do not lose much security, but we gain a lot of performance increase. We have a question.
Security often goes back. So
Yes, it's 4-dimensional. In this case, we're dealing with a 4-dimensional vector, so this is the reason why it's shown it this way. And this, we generate one vector.
Yeah. So there is a relationship between M and N, and N is the Decision function. The Decision function of N. So when M is the power of 2, is half of M, basically. That's I believe, right?
Yeah. In this case, I think it's more of a conceptual illustration showing multiple polynomials that are generated. So to generate one polynomial on the right-hand side, in other words, the first 4 components, they used one vector, then simply went through all the coefficients, and the idea is you generate only one vector to get the result, only one vector as the result. Yeah, I think it's maybe a little bit confusing the way they illustrate. I would say it's more of a confusion on the representation. You can just keep in mind that we have the first 4 rows, and let's focus on those because they're just trying to show multiple vectors in this case. And what I mentioned about the security of ideal lattices is that there's some reductions, quantum reductions, that relate learning with errors problem to approximate shortest vector problem formulated for xn+1 ideal lattices. And so that basis is what we use from the security perspective, what allows us to use ideal lattices.
So quantum reductions, I'm familiar with that. Do you mean quantum computing reductions, like linear time quantum computing reductions? Is that what you mean, or is there something else?
It's actually related to probabilistic methods when you perform the reduction and you use probabilistic methods to go from one to another. So that's what it means.
Okay. So it's basically from our already exists.
Yeah, it already exists. Yeah.
Okay. Yeah.
But generally speaking, there is this problem for xn+1 ideal lattices is equivalent to the learning with errors problem, and that's what allows us to use this more efficient scheme. And now a little bit more at the Ring-LWE formulation of that same learning with errors problem. But now we're dealing with polynomials. Now understand those ideal lattices are equivalent to polynomials, so we actually can use those two interchangeably from our perspective. And I think polynomials are easier sometimes to grasp from the computer side. but ideal lattices are easier to implement on the program side. So what is, let's refresh. What is the problem that we're, what is the kind of logic behind Ring-LWE? So given the G1, now it's a vector. So remember, it used to be matrix, now it's a vector. And put the following vector, G multiplied by S plus 1. All three points here are actual polynomials, and particular polynomial is generally referred to as noise polynomial, and often it's often referred to as small polynomial, which means that it's generated using that discrete Gaussian distribution with a certain bound. And
so computationally, at least implementation-wise, because these things are so each GI, each EI is represented as a vector.
That's correct. Yeah. As an ideal lattice, which is a vector.
Yeah, which is computationally represented in computer memory as a vector during implementation.
Simply speaking, when you deal with the coefficient representation of polynomials, and so far that's all we've covered, any polynomial can be represented as a vector with the coefficient basically listed as the components of that vector. So the coefficient vector, we can just simply call it coefficient vector. There is another type of representation, but we'll touch that topic a little bit later. And the second secret polynomial. So this S is related to the secret key that's involved in crypto schemes based on Ring-LWE. There's like a couple of different ways to generate that polynomial. It can be selected as a random polynomial, or it can be generated the same way as a noise term. So we'll discuss those differences. Mathematically speaking, they're equivalent. And what's hard about this problem, when you're given both of those vectors, and I'll just use or polynomials, no matter how, what term you use, it's very hard to find the components of vector S. And actually, the components of vector S, you also have to find the components of vector E, but you're given this, and then you're given a polynomial, and engineer and get the value of S is a mathematically hard problem. And to illustrate this, there is a formulation that we looked at in the previous slide is solution-based formulation. It's a solution problem. And then very often in the analysis of NP hard problems, we all look at the decision problem. And so it's really they're somewhat equivalent. And the idea from the decision perspective, that let's say you are given two polynomials, G2 and, let's say 1 and T1. And the polynomial T1 or vector looks random. So you don't see any patterns in the components of vector T1. And the idea behind the decision formulation of Ring-LWE is to prove whether this T is truly random, it was generated just using some pseudo-random generator, or whether it was generated by the performing operation of polynomial multiplication and addition. So in other words, using those three polynomials, determining which way it was generated. Is it truly random, or was it generated using this technique? That's what constitutes the decision problem. It's something that looks totally random. So if it's random, you don't even know whether it randomly generated or it was generated using this scheme. That's the idea behind the decision formula of Ring-LWE. And those two can be shown that those two are equivalent. So trying to solve the problem of finding S, and this is the solution formulation of the problem, is equivalent to the problem of when you're giving random A and random B, trying to figure out whether they're just simply random or they were generated using a special process, and the process is driven by the Ring-LWE problem. Illustration of this fact that when we try to solve the problem, we're actually going back to the decision problem. And the decision problem is what makes it hard for us to find S, because it looks totally uniform.
Uniform, which means it's not quite uniform. The amount of information you actually have is efficient to actually do that diagnosis.
Yeah, the way to formulate it from the practical perspective. So now let's look at those ideal lattices more in terms of polynomials. And the reason why this will be important is first we'll look at the Ring-LWE problem from a different perspective. Second, we'll also introduce the concept of evaluation representation of polynomials, which will be important. So, we have a middle ring, and when the ring is formulated as Z with the subscript of QS divided by xn plus 1, this means that we have two modular operations, just like Kurt noted earlier. We divide the polynomial, we perform the modular operation for Q, and we also divide whatever polynomial we have by xn plus 1. So in other words, we have double modular operation as part of polynomial ring. That's what this notation means. Polynomials, represented the standard polynomial representation. In this case, it's a coefficient representation that I'm sure you've seen many times. The only difference is that the actual values of coefficients d1, d2, etc., are integers and integers mod q. So integers in the certainly up to q minus 1. For polynomials is performed using wise addition or component-wise addition. In other words, when you add two polynomials together, you simply add the corresponding coefficient. So very simple operation, and it's easy to perform it efficiently. Application of polynomials is a little bit trickier if you deal with coefficient representation, because you have to multiply one polynomial by another polynomial, which implies that for each component you'll multiply it by sum of the components of other polynomial, and then you need to perform modulo xn plus 1 operation. So for us, there is another way to perform this multiplication using where the product can be computed using component-wise multiplication. So you just multiply two corresponding components. But we'll show how that's going to be possible. To give you a simpler example, let's look at the case of Z17 divided over x to the 4 plus 1. So in other words, our dimension in this case is limited to 4, and our modulus q set to 17. So it's very simple. And what it means is that we will have here with the maximum power of 3, and each in this polynomial representation will never be larger than 16. So that's just it's an integer going from 0 to 16, whenever is possible when we select mod 17. So simple example of polynomial with 4 dimensions. And this 4 is very often called in the literature as ring dimension. Just something to note, because you see that term in a lot of crypto papers. It's a ring dimension, and that's what it means. It's really the dimension of the vector that you will be dealing with. We look at the Ring-LWE problem in terms of polynomials. You have two polynomials. One is polynomial G, and another is polynomial T. And this polynomial T was generated using polynomial S and E, are unknown, which are in a sense prime. it. And when you're given those two polynomials, how do you find this particular polynomial? In other words, how do you find the coefficients of these polynomials? So this is a polynomial formulation of that same problem that with the Ring-LWE problem that I looked at in the case of ideal lattices. All of these operations can be transformed to simple polynomials. And probably conceptually, intuitively, they make it a little bit easier. In that sense, those of you who are well familiar with this discrete log problem, this operator finding S is somewhat similar to finding the discrete logarithm in the case of elliptic curves. So, and we can formulate a decisional version of that same problem in terms of polynomial. The same idea is to differentiate between two random polynomials and two polynomials where the first one was random and the second was generated using the Ring-LWE problem. So again, this is just the same problem, but played in terms of polynomials, which are probably a little bit easier to understand. Getting to the next point, so in addition to the coefficient representation of polynomials that we've discussed already, there's a so-called evaluation representation of polynomials, which makes it possible to perform polynomial multiplication component-wise. So, and the idea is that instead of dealing with the conventional polynomial multiplication, we can simply multiply the values of the vector representing the polynomial and get the result immediately.
So this is some context, because this is pretty important, right? So some of the context for this is, and please help me expand on this a little bit, Yuri.
Sure.
That big part, one of the functional advantages of Lattice Crypto is the ability to support what you call homomorphic encryption schemes, which is that you can transform cipher into a notation where you can form computations on that ciphertext. And this remainder transform is somewhat analogous for those of you like me who come from more of an electrical engineering background or probably familiar with signal processing. That signals that might be, for example, a time domain and put to a frequency domain and then run a lot of filters and manipulations on that data much more efficiently in the frequency domain than you did in the time domain. You've heard things like the discrete Fourier transform and stuff like this. And this analogous to something like that, where you're taking representation in what's called power basis and forming it using these Chinese remainder transform into what we call Chinese remainder basis, the Chinese remainder representation. These kind of transforms that we've been talking about all along. And you can start to do these components much more simply in what they call the Chinese remainder basis. They have been able to in the power basis. This is actually one of the reasons where I know stuff can be sometimes kind of dry. This is where the reason kind of why we're getting at this kind of stuff is because these kinds of things that Yuri's going over exactly right now. Sure. Yeah.
Yeah. So just for terminology's sake, so evaluation representation is also often referred to in the literature as CRT representation or Chinese remainder representation. So when you see CRT, single CRT, that's evaluation representation. It's exactly the same. And coefficient representation and power basis also, they're interchangeable. So just because depending on the paper, you'll see different concepts used, but it's very important to understand that what we're looking at is the CRT or Chinese remainder transform representation of polynomials. The evaluation representation.
I just happen to use Chinese remainder or power basis terminology because I learned a lot of this from Chris. That's what he uses. And sometimes, maybe this shows the hierarchy of where people learn these kind of things based on the terminology that they use.
The conventional mathematical literature, it's usually coefficient and evaluation representation. Okay, so what's the advantage? I'll quickly go to the advantage of using this, and I'll try to explain how we use how we actually find the values at which we can compute the polynomial. So the reason why we introduced this represents that when we perform multiplication, we're just multiplying the components of the vectors, not perform multiplication of one coefficient by a sum of their coefficients in the second octave. All we're doing is we're just multiplying the value of the polynomial at a specific point by the value of the other polynomial at that point. So that's all we're doing. This is why, from a multiplication perspective, this operation can be done in component-wise manner. This is the reason why the representation is used efficiency. Polynomial multiplication can be done in an efficient manner using representation, CRT representation. The second important question is what are the values of that we should use to represent the polynomial? And what we're doing at those values, we actually compute the polynomial for those arguments and use those results of the equation of the polynomial as to form the vector. These are actually correspond to primitive roots of unity. So certain special numbers, and we'll discuss in more detail the definition of those numbers that can be computed rather, in a relatively efficient manner, or at least they can be pre-computed, and then all operations afterwards can be performed using those known primitive roots of unity. So the problem of finding those roots of unity and you use them to, for example, perform the Chinese remainder transform. So it's just to illustrate the idea when we deal with Chinese remainder representation, when we have the operation of adding two vectors, we're adding the values of two vectors at those primitive roots of unity, 2, 8, minus 2, minus 8, and we perform the multiplication. We do the same thing, but with just multiplication. So polynomial multiplication is done in an efficient manner. Just another way to illustrate it. So this is how the polynomials are stored in this case. We simply store their values at those primitive roots of unity. These primitive roots of unity that we choose, and we'll look at an example of x 10 to the power of 4 plus 1, related to the so-called concept of cyclotomic polynomials, and those they're called irreducible polynomials. And these cyclotomic polynomials play a very important role, and all the operations that we perform on ideal lattices are done for those cyclotomic polynomials. And those cyclotomic polynomials satisfy the property of irreducibility and certain other properties. And also, the other advantages of those cyclotomic polynomials is that the roots of those polynomials correspond to the roots of those polynomials correspond to primitive roots of unity, what we discussed, so the concept that we discussed. And the general idea when to find, there is a procedure to find primitive root of unity, which I'll briefly discuss there, but if you have a certain root of unity, that you can easily generate all other roots of unity that then can be used to form the conversion from the coefficient representation to the evaluation representation. In other words, to compute the discrete Fourier transform or to compute the Chinese remainder transform. And so those operations are done in terms of the roots of unities, which are directly related to the definition of cyclotomic polynomials. And simply speaking, if we polynomial of x to the power of 4 plus 1 mod 17, the that we looked at, the
Pausing point. I want to. Just a second, but please.
and actually we only have 2 slides left. So
Sure.
The next one, and I think will be ready then. So in this particular case, for the polynomial that we're looking at, x taken to the power of 4 plus 1, the atomic order is actually 8, and we'll look at some examples why it's that way. But the atomic order of polynomials, in this case, is always a power of 2, and the polynomials themselves are formulated as x taken to the power of 2 plus 1 as well. And primitive root, simply speaking, means a function value of omega, in this case, for the order of 8, that omega taken to the power of 8 is stronger to 1, but when it's taken to any smaller powers, it's not equal to 1. So that's what's considered as a primitive root. And once you find that primitive root, you can easily compute all other primitive roots that are used for the representation of polynomials. So you don't need to compute all of them. You simply compute one, and then you can use that one to find all the values that you need to use to formulation and presentation of polynomial.
So I think we're going to have one lecture, based on the conversations we had, and then I spent a late night a couple days ago going over the FFT. The FFT is kind of this very basic algorithmic context construct that's doing a lot of these linear transforms. And although lots of electrical engineers and computer engineers learn the FFT in terms of real-time signal processing and things kind of like that, particularly manipulations in the complex domain, what we found is that basically almost all the math carries over almost exactly. And so, whereas a lot of these equations that Yuri's going over are all in terms of modulus arithmetic and things like that, the exact same math that works from the complex manipulations are also in here also, which is one of the reasons that we use these FFT type constructs and one of the reasons we like them so much. And particularly the team I was running for DARPA, why we actually were able to get things running so fast on FPGAs, was basically because we were able to take a lot of this stuff full a lot of existing math and algorithms and basically sprinkle a little of mathematical modulus stuff on top of everything and make it work. It's actually a little more complicated than that. It took some years, but conceptually is why we're able to justify it to our patrons at the time. And so I had a quick text conversation with Henry over in SSCPAC, and he was had a couple questions, wanted to clarify some things about this DX transformations and whatnot. And so the text I just sent to Henry a little while ago to answer his questions was basically that if you think about how we use the discrete Fourier transform, which is a discrete version of the FFT, fast Fourier transform, the time domain to the frequency domain, and we use DFT to go back from the frequency domain to the time domain. And there, we'll have to put this, wrap this up in a slide so that it's actually have it something that I'm just saying verbally, is that the Chinese remainder transform from power basis to its remainder basis, CRT inverse to go back. And that T is basically a DFT with some indices removed, so that a lot of these FFT-like constructs and implementation. So basically the CRT is referred to as a representation, and then in essence, and so the terminology is basically a little tad overloaded. So sometimes you got to be, for those of you that are following along at home, you got to pay attention to those kind of uses of the terminology in context sometimes. So the lecture I think is going to focus almost exclusively on the CRT and double CRT and the implementation aspects of this. Particularly they impact the FFT also. That in a second. So
this is actually the last slide of our today's presentation. And what I wanted to note is that the choice of that atomic polynomial, the polynomial that we divide by in when we talk about ideal lattices with x and pi plus 1, those were the examples we considered so far, is actually very important. So the easiest one to implement and the one that has a lot of proofs, mathematical proofs, is the choice that we discussed. So in other words, the power of 2. So when the cyclotomic order of 4, that corresponds to the polynomial x squared 1. When we have the atomic order of 8, that corresponds to x taken to the power of 4 plus 2. So those are the examples we've looked at in this presentation, and those are the easiest ones. And this will be the first scheme that we're going to build will be based on this power of 2 cyclotomic polynomials. There are other types of polynomials, and in the general context, in mathematics there is a concept of arbitrary cyclotomic polynomial, which means any one of this, regardless of whether it's the power of 2, whether it's prime, or any composite number. And there is a paper actually showing that it's possible to perform operations using arbitrary cyclotomic polynomials, decomposing those arbitrary cyclotomic polynomials in polynomials with prime cyclotomic orders. In other words, the prime ones would be something like for the order of 5, for the order of 3, for the order of 7, they have a certain presentation. So generally speaking, this problem can be solved for cyclotomic polynomials, and supposedly this will make it much more efficient, because when we deal with power of 2 polynomials, you're dealing with a sparse representation. And in the case of arbitrary cyclotomic polynomials, you'll be able to use, for example, a search in a more efficient manner. And one of the papers that we'll probably discuss in future lectures actually talks about the techniques how that can be achieved. But simplicity's sake, so we're looking only at the power of 2 cases, such as the case of power of 4 or the case of 8. Right. So that's the lecture.
Well, thank you, Yuri. Starting a little bit over, and maybe just say that, proportions, in case people need to run off, maybe we just talk about what we're going to do the next couple weeks or so. Next week is, well, 2 now, and I think a number of people from San Diego are going to have to go to the Proceed PI, or have to go. We are looking forward to going to the Proceed PI meeting. And so maybe we'll go into hiatus then, because I won't be here and a couple of San Diego people won't be there. I think it's also going to be midterm times also for around here also. So, but what about that? But for next week, and for those of you in San Diego, maybe you should unmute your mic for a second, because I got a question for what you guys would prefer. Yuri and I have been working on this proxy re-encryption scheme with Vinod Vakanathan from MIT. And in some sense, it's one of the simplest lattice crypto schemes that actually does something that's more than just basic public key crypto. We were thinking about, it's basically the easy way from the math into actually getting things built, thinking about possibly giving an overview of the taxonomy of lattice crypto systems. Like there's NTRU based. I know you guys in San Diego are building up a variant of BGV, I believe. Mm-hmm. And then we have this PR scheme, which is a variant of NTRU. And maybe we should just give a brief survey of lattice crypto systems. I think it'll be very good for my students here, the students here, and then kind of give an overview of PRE, basically to kind of give a look and feel for how we actually build crypto systems from these various mathematical building blocks.
I think sounds good.
Okay, then maybe that's what we'll do. So, some of the stuff that we've been doing so far has been fairly dry mathematics, but get into some of the more meat and potatoes of actually building crypto systems and used and what the various trade-offs are, so we can then dive into meaty parts of like the CRT and then some of the more AES type applications and other research papers from there.
So do you want to proceed with the survey? I mean, do you intend to do that, or how are you planning to do that?
So I think in terms of survey, I think it was more just presenting a taxonomy of how these various things are put together. We'll put together some material on our side. My particular expertise is on the NTRU type systems and how those. But this is the reason we couldn't make this interactive thing. If after we go through it, you guys can talk about some of your experiences at a high level to try to make it a little, start to make it more of a two-way conversation.
Okay.
I would invite you. I'm not necessarily going to force you to, but this is the way we want to run it, right?
Yes.
So maybe how about we just trade email over it? Yuri and I will put together a rough outline of maybe what we think would be good for about an hour conversation. And if you guys want to take part of that, or if you want to maybe have a full session later on to talk about some of your work or the schemes that you guys are doing, that might be just as good also.
Yeah. So let's do that. Let's continue the conversation. Yeah.
Okay. So like I said, I know we've been going over a little bit. Folks in San Diego or folks here in Newark, any questions or comments? San Diego.
I myself don't have anything.
Yeah,
Okay.
that's been excellent. Thank you. Thank you, guys.
So I have one question from one of our actually brave undergrads who decided to show up.
Not much. Just keep going to slide. I want to see what's really.
Sure.
So this 17.
Oh, it's a prime. So it's a prime.
Small prime. That's
It's a
not
small
great.
prime. Yeah, it's a small prime that's easy to, we can perform basically. We can study examples using that small prime. But in reality, we would just be dealing something that has like 30 bits. It's a prime with 30 bits. So that's what we'll deal with in crypto schemes.
So, Chris, somebody following on. Sorry, go.
About I think it's slide 8. It's the slide 23 on the if you have them both together, but use the same efficient idea is the title of the slide. Has the 2012. Is two vectors that are represented in that m by n matrix?
So those are two vectors. So one vector A, another vector B, and equivalently, you could call them two polynomials. Yeah.
Okay, polynomials, and then they just been cyclically shifted up to various.
No, it's just two polynomials. So let's say you want to perform certain operations all over those polynomials, such as multiplication or addition. And you have a polynomial A, you have a polynomial B, and then you would perform those operations. Yeah.
Okay. Polynomials represent a lattice, or are they two vectors that act as basis vectors for that lattice, or are there? I mean, what's being represented by that n by n matrix?
Yeah. So the let's say AX polynomial simply represents a vector in the ideal lattice. So just a vector in that lattice.
Okay.
Vectors that can be represented as a linear combination of basis vectors. In other words, I mean, if we go back to our original definition, just a vector that's in that lattice in a sense. Just
Okay, so I really want to handle this one because this is the nature of me coming from electrical engineering. I get all kinds of worked up because my used to be in stochastic modeling and probability distributions and stuff like that. So when people generally say the word random, people that have some probability or stochastic modeling yet, which you will if you're going to be my PhD student. When people generally talk about random, they mean uniform, which means any set of outcomes is equally likely. Like a flip a coin, heads tails is equally likely. That's what's a uniform distribution, a uniform sampling. Other kinds of distributions, and particularly discrete Gaussian, which I've been talking about with a couple very recently, where they have this non-uniform distribution, where things are more likely than others. So, yeah, that's for everyone.
Yeah, I'd like to make it from
Sure. Line, please go.
Yeah, I would say maybe we can have maybe some slide on uniform distribution for people to understand more about it.
Sure, you have to go over, especially because go.
Yeah, but maybe the randomness, how do you generate a random, what to make something to be real random number.
Their engineering.
I think actually I would really like to take that on and have maybe just have one seminar that talks about random modeling, random generation, uniform, and I'm kind of busy with getting things ready for the PI meeting in 2 weeks. So maybe the week after the PI meeting, I'll have put together a real solid lecture about random modeling and random number generation.
Okay. Yeah, that'd be good.
Sure. Sorry,
yeah, just more mathematician in me. I wanted to make a note about uniform distribution and uniformly random distribution, because uniform distribution in mathematics may mean just you have numbers with the same values in a sense. Uniformly random makes sure that that the random numbers are chosen uniformly. This is why it's just uniformly random, because those. So, strictly speaking, that's how you want to define distribution.
Yeah, so all different topics I want to talk about sometimes. But yeah, okay. So, online.
So if you go to the next slide, the value of omega. No, not the previous.
Primitive roots of the
Yeah.
This one? Yeah.
So after we find out the value of omega, I mean the value of omega should be, there should be only one value, or there are many values.
There are multiple primitive roots of unity. In this case, we have 4, and you simply need to find one of them, and then you can generate others.
How to generate the others?
And this is an example. So you simply you take the prime, you take the primitive root and take it to prime powers. I mean, prime powers to be. When you compute it for co-prime powers, and 3, 5, 7 are the examples. In this case, you get all the other primitive roots of unity.
Right. So co-primality is very, very important. For a lot of different systems we're dealing with, and particularly its Euler-Toshens function. There's a lot of stuff that goes into number theory associated with the computation of these kinds of things, and it's one of these. There was years ago someone was obsessed with a certain number because it was just such weirdness. It's kind of like Lattice Crypto seems to obsess about co-primality and Euler function. In a similarly weird way. So you see it pop up in a lot of weird places. But yeah, it's particularly important for dealing with these kinds of things and the different roots of unity. So, folks in San Diego, good people here in Newark, thank you very much for your time, and we'll trade email about talking about next week.
Yeah, very good. Thank you.
Thank you, everyone.
All right. Have a good day.
Thank you.
Bye.